So once again, I want to welcome all of you to the Valley of the Shadows of Statistics for Business Analytics or Data Science. We want to look at probability, particularly probability methods. Remember that until what you know becomes what you do, you don't know anything. Until what you know benefits you and someone else, what you know is useless because the evidence of knowledge is result. You cannot tell me that you are a person of knowledge when that knowledge is not reflecting in your result. So my goal is for you to have some knowledge on probability today. Based on that knowledge, you can understand and be able to help other people with a concept of probability. Now, let's begin by myself giving you the objective of our study for today. By the time we finish this seminar, you should be able to explain the basic concept of probability to anybody. Now, I'm going to teach you this as if you don't know about probability. So if you already know certain things about probability, do not rush. Ask yourself, how can you teach someone this so that a person will benefit a lot? And by the way, please put it on the page, let people know that we are live, okay? And please, for those of you who have still not subscribed to the channel, please do that. And when you get a video, you also acknowledge or like it so that I can increase the algorithm for this. Okay. I also intend to use a bit of Venn diagrams. I hope you remember the whole story of Venn diagrams. Mukai, you remember Venn diagram? Okay. We are going to use a bit of...
Yes, sir.
Excellent. We're going to use... You see, when you are able to communicate and respond to me, it helps me to know that you are here. You see, you are looking at me, and so you feel much more comfortable than if I'm hiding. And since I'm not looking at you, the only way I can know that you are with me is when you are interacting, when you are commenting on the chat and all of that. Okay, you'll be able to apply some rules of probability. We shall learn 5 rules of probability. You'll be able to compute conditional probability, and you will know that it's not just conditional, it is applied. I will give you an application of the conditional probability. And then we will look at the Bayesian probability. We'll look at that. And finally, I'll give you just, if there's time, I'll give you just a bit of introduction to random variables. So like I said, I'm going to go quite slow because I know that, you know, brevity is essential. Okay. And Leonardo da Vinci said that simplicity is the ultimate sophistication. Simplicity is the ultimate sophistication. So I'm going to be quite simple so that you'll be able to understand than being complex. And then you don't understand. Okay. So what is probability and why do you study probability? Well, I will answer the second one before I answer the first one. Why do you have to study probability? Because certain conclusions you make in life depend on what you had before. You saw your wife with another man and they were holding hands. You saw them from the back and you concluded that your wife is cheating. Later on, you got to know because you saw them from the back and that was the sample you took. You didn't see them from the front. And so that wasn't the sample you took. And based on that, you judged, you hypothesized that your wife was cheating. When in fact, if you had gone in front, you would have seen that the man was his blood brother. So conclusion can be wrong based on what you see. Another example. If you are standing in front of me and I write this number here, what number is that? What
Is
number?
that six?
Six. Six.
Okay.
6.
Well, to be honest with you, if you are in front of me, the number is not 6. It's 9.
9, sir.
Depending on where you're standing. So how you see things is based on the sample that is in front of you. And probability is the chance of an event occurring, the likelihood of something happening. And so you can conjecture that something is going to happen based on what you have at hand. And it could be wrong. For example, do you think it's going to rain tomorrow? Do you think NDC will win the next election? What is a sample in your hand that is making you conjecture, guess, hypothesize? Do you think MPP will win? Do you think the Democrat or the Republican will win the next election? We need to know the chance of an event happening. We need to know. We need to know. And that's why we study probability. So probability is very important, not only in academic. You can predict the stock market, whether it's going to collapse or not going to collapse. And that's why you have to understand, when you study probability, what it does is that it helps you to know the amount of salary you are getting, whether that salary can make you a millionaire. And another person can have the same salary and the person will be broke in 25 years. But then, by virtue of probability, you'll be able to know which derivatives, which financial engineering, approaches you can use to be able to maximize that income you are getting. The chances of you multiplying the income is probability. You can use probability to even win a girl. You can use a probability to determine whether or not you are going to pass the next exam. And we shall do a couple of examples. That's why we study probability. Ladies and gentlemen, does that make sense? Does that make sense before I proceed?
Yeah, it
Yes,
does.
please.
Yes, sir.
Now, let's get the real deal. What is probability? And what is an experiment? I've said it already. Probability is the likelihood of a phenomenon happening. And when we talk about happening is not usually now, isn't it? It's usually tomorrow. Even if it's the next 2 minutes, it's still tomorrow. It's still more or less a future thing. So it's more or less a long run relative efficiency of something. Probability is not immediate. It's not instant. And instant, again, is by definition, whether you're talking about seconds or hours. What is the probability that by the time the lecture finishes, you know you're going to get A? So it's a long run relative frequency of something. How something is likely to happen because it's happened multiple times. That is probability, the chance of an event happening. But before you can actually do probability, you need to conduct an experiment. And by experiment, we are looking at a process that is performed in order to understand and observe the outcomes of events. So an experiment can happen in your brain. An experiment can happen physically. And based on that, you observe. And based on that observation, you'll be able to come out with some conclusion and then use those conclusions to predict or to hypothesize or to determine the chance of the next event happening. But you are a master student. And because you're a master student, you got to know certain symbols and certain terminologies. And so there will be some kind of mathematics to be able to appreciate probability. If you were an undergraduate student, it will not be flooded with a lot of mathematics. But you're a master student and you are supposed to become PhD students later, doctors. I see you guys as doctors. Even if you don't see yourself as doctors, I see you as a doctor. So because I see you as a doctor and I see you as a future, powerful beings who are going to transmit knowledge to people, I want to bring a bit of mathematics to it. So do not be shy. Do not be worried about mathematics that you are going to see. The ones you see on your screen right now, just keep them. This symbol is called omega. And then you have this sort of F symbol, which basically is going to refer to an event. And then P sort of is going to refer to the probability. So let's first look at the probability space. Suppose I want to look at the probability space. What is that space? Well, that space is made up of the sample space. It's also made up of the event within the sample space, and it's also made up of the probability of any of the events happening. So this is the structure of the sample space. The omega is a sample space. So if you can remember Venn diagram, okay, when you draw a Venn diagram, a rectangular Venn diagram, that whole thing is the omega. And it is a set of all possible outcomes of any experiment that to be done. But what then is the event? The event is the collection of a subset of the sample space. So the event is a member of, is part of the sample space. Now, it could be that the event is a whole of the sample space. Or it could be that, and when I say the whole, let me draw it for you. It could be that, okay, if this is a sample space, okay, this is omega, it could be that the event is the whole. It could be that the event is the whole of this sample space, okay? And so the sample space is more or less the same as the event. Or no, it could be that the event is a portion of the sample space. Okay. So that is why you will see that I have this symbol being a member of or being less than or equal to the omega. Okay, that's me. I know you get it because these are basics. Now, the word P is going to be used to measure probabilities. When we say probability, we are talking about the P. Okay. It is a function. It depends on the event. And this probability is between 0 and 1. So the value of any probability is supposed to be between 0 and 1. And it assigns that probability to each of the event. So whatever event, and by the way, in the sample space, there could be a lot of events. Okay? For example, when you have this sample space here, this omega, there could be that event, there could be that event, there could be this event, there could be this event, there could be this event. So there could be a lot of events within the sample space. And you can have a probability measure for each one of these events. So these are some key terminologies you got to note before we even start the game. Now, if the event contains any set, and I'm going to describe the event further. If the event, okay, which is this, contains a set, then it also contains the complement of the set. I'll give you an example for you to appreciate it. What is a complement of an event? We'll look at it. But who can tell me? What is the complement of an event? So if you have an event, okay, if you have the omega, and then you have an event called A here, okay, and this shaded A is the event. what is the complement of this event? And by the way, the complement of the event is written as a to the power c, or a to the power prime. That is what we mean by the complement. Raise your hand and please tell me, what is the complement of the event? William, entry.
Okay, so actually it's going to be those elements in A, which those elements in the universal set or the big set, which are not in set A.
Good. So where would that be in this graph, for example, that I've drawn? What would you mean by
So
that?
it will be in the empty part of the triangle.
Okay, the empty part of the triangle. So you're talking about anything that is not in the circle but is inside a triangle.
Yes, please. Yes, please.
Very good. That's it. Anything that is not in the circle but is inside that. Now, the way we write that complement is a to the power c or a prime. Okay, so just note that, because we'll be using some of these a lot in our work. Okay, now let's look at some experiments and possible events. Simple examples. If you toss a coin, okay, the entire sample space, the omega, is going to be you getting a head or a tail. There is no way you will not get a head or a tail. It's either one of them. And that is a typical example of an experiment with this event. If you throw a dice, okay, a dice has got 6 sides. Then the omega, or the sample space, is each of these events happening. Event 1 can happen. Event 2 can happen. Actually, there is an event that can also happen, but we normally don't write it. And it is the empty set. Okay? The empty set is the empty set. That is a possibility when you decide not to throw the dice at all. Okay? So we normally don't harness too much on that, but just know that that is also a possibility. But these are the events that can happen in each of these experiments. The percentage of the probability within the entire sample space is going to be between 0 and 1. 0 and 1 being inclusive. And of course, you will note that then the 0 is going to be the empty set. Then the time measurement, that is for each of the events, will have a positive probability of it happening. And this is a positive real number, or real positive all times that you see there. So there is a range by which the probability of any of the events happening is, and that range is between 0 and 1, or is simply 100%. So these are some simple examples. Now let's try to understand events using Venn diagrams. And we should look at them mathematically, but I want you to enjoy them, understand them first. For example, events combinations can be union. So you can have the union of events. You can have event A, and you can have event B, and you can have the union of that. Now, let's try to see an example here. So here you have event A, and then you have event B. Now remember that I have not shaded the circle between A and B. I haven't shaded it. And so I am looking at the union of A and B. Now later on, I'll look at other things, but as you can see, I'm looking at the union of A and B in this context. Yes, William. William, your hand is up.
Sorry.
Let's move on. Now, if another combination you can have of events is intersection. Please note this. If you are taking notes, write this down. That intersections are looking at the joints of the event, the joint event. So the intersection between A and B is a shaded area here. And this intersection between A and B is just indicating certain factors that are inside both A and B. And we shall be giving examples. These are all possible combinations of events. Remember, we are looking at combinations of events. And this intersection is the same as the union, the joint. So that means that we have this joint. This joint is also called mutually exclusive event. So here you have A and B, but then they had an intersection. And now you have A and B, but then they don't have an intersection, which means that A and B are mutually exclusive, which means that they cannot happen at the same time. Right now, you cannot be having the lecture and at the same time be attending to a funeral in a different location. You can't. Okay. Maybe you can have your phone and blah, 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 but you cannot do both at the same time. You will miss some of them. So these events are said to be mutually exclusive, or they are not joint, they are disjoint. And this is how you represent them by Venn diagram. Then you can also have complements, okay, events that are complements. And you can see that A is in the circle and the complement of A is a red area. And these are known as complement. We've looked at complements already. And then you can have this where you are now taking consolation from A and B, but then you are taking the intersection out to be able to handle A and B separately. We'll come to that in the process. Now, if you look at this very one, it's a little bit interesting. You can see that B here is a subset of A. And so you can see that the whole of B is inside the whole of A. Now, what will you call this? You can tell me. What will you call this very one, where the whole of B is contained in the whole of A? What do you think A union B is? What do you think will be A union B? Salasi.
So A union B will still be A.
Salasi, you sound far away.
A union B will still be A.
Exactly. A union B is A. That is A union B. And so you should be able to use Venn diagram, because Venn diagrams, they help us to see the relation, to see the relationship existing between events. Now, if you look at this, that is the same one that I showed you, okay, here. But you will note that A union B can be rewritten as this. It is the same B union A, but the A intersection B complement. I mean, you can see that. Okay? Because B complement is everything that is outside of B. And A's intersection with that is a union with B. A's intersection with that is a union with B. Okay? I'm just giving you multiple ways of using Venn diagrams to help you to get the picture. We've already looked at mutually exclusive events, which are disjoint, and then non-mutually exclusive events, which are joint. All of these events can be represented using Venn diagrams. Okay, now let's get a little bit deeper into probability. Okay, an event on a sample space satisfies the following conditions you're going to see. Just look at these conditions as now. If you don't understand, you let me know. Okay. For example, this event is a member of the sample space. It's part of the sample space. You cannot be an event unless you are part of the sample space. The probability of an event happening is always between 0 and 1 inclusive. It's always between 0 and 1 inclusive. And then any particular event is a member of the event set, which will mean that any particular event that is not an event is also going to be a member of the event set. I mean, you saw that between B and A in there. Okay, so anything that is not in B is also in A. Now let's look at axioms of probability. By the way, axioms simply talk about certain things that must be there for certain things to work. For example, if you say that the university has started, the university is running. Once you say that the university is running, then automatically you've assumed that students are there. You've assumed that the lecture rooms are ready. You've assumed that the board is there, the computers are there, the duster is there, the markers are there. All of these are assumed, they are axioms. So axioms are certain things that must be in place for certain things to work. For probability to work, the following must be there. 1, the probability that an event is occurring is written as this. It has to be positive, but it can also be 0 because it's not occurring. The probability that an event is occurring is positive for all the events that are within the sample space. This is one of the axioms of probability. The probability of the entire sample space is 100%. That must be there. Okay? That must be. So the entire omega, okay, the probability of you getting the entire omega is 100%. Any portion of that sample space is a probability measure. It's below 1. If those two above are happening, then we can say that if you have a probability of any event happening, where the event starts from 1 all the way to infinity, and any of these events is part of the probability, is part of the event set, given that, or for every event where the event I is not the same as event J, okay, then we can say that the event A within the I, its intersection with event A within the J is an empty set. We know this. If that also holds, then it implies that the probability of the entire union of each of these A's is going to be equal to the sum of the entire probability of each of these events. And that is why we can say that the probability of the empty set is 0, which we said already that it is possible for any event's probability to be 0. It's possible. And therefore, the probability of the empty set will be 0. If the above is happening, then the probability of the empty set is 0, because if the above is happening, it means that something is happening. And if something is happening, then the probability of something not happening is 0. These are the axioms of probability. Now, you may not fully understand the third one mathematically, but it simply means that events are happening. That's all it means. Events are happening. Multiple events are happening within the omega. And if multiple events are happening, then multiple events not happening is 0. Now, watch this. The omega, it includes certain things, 2 major things. Let me draw it for you to see. This is the omega. It includes the space plus the line. I want to repeat that. It includes what you see as the space plus the boundary of the space. This is what is known as the probability space. So I want you to know that the probability space is not just the space, it's the space and the line. It's a basic thing, but it's a very, very important thing for you to appreciate. Let's look at the rules of probability. It's a very simple rule. Okay? And I know I've taught you some of these things before, so let's look at them very quickly before we go to the real practicality, the usefulness. Because you see, one of the things I've seen is that when people are learning probability, then they are a little bit afraid or shy, or they wonder whether it's meaningful. It's meaningful. It's meaningful. The first rule of probability is known as the complement rule. It's very simple. We've looked at it already, but we're only writing it mathematically. The probability of the complement of A is 1 minus the probability of A. It's a very simple thing. So if the probability of A is 0.5, then the probability of the complement of A is looking at the probability of things that are not inside A. And that is 1 minus 0.5, giving you 0.5, because the entire probability space is equal to 1. Now, this complement rule is a beautiful rule, but the addition rule is even more beautiful, because the addition rule looks at the union of probability. Now, using the addition rule, the probability of A union B, it can happen in 2 ways. The first one is when the events are joint, and the second is when the events are disjoint. When the events are disjoint, and I hope you understand, I'm talking about mutually exclusive and then non-mutually exclusive. So let's look at the situation where they are mutually exclusive. When the events are mutually exclusive, it means that they are separate from each other. So we can say that the addition rule says that the union of A and B will be the probability of A plus the probability of B if A and B are mutually exclusive or disjoint. But if they are joint, that is when the circles are meeting. Then the rule says that then the union of A and B, the probability of the union of A and B is the probability of A plus the probability of B minus the intersection of the probability of A and B. Okay, or minus the probability of A intersection B. This is the general one. Now, I want to ask you a question. Why do we need to do this minus the probability of A intersection B? Why do we need to do that? What is the essence of that? What is the essence of that? Why do you need to take out that probability of A intersection B? I need to get some smart people talking to me. See, I've been talking, I need to feel you. I need to feel you. Let me tell you something. If you are here and you don't understand a little bit of anything, you ask. Get a point? A little, I said a little. That way, it helps you to understand than the ones that are not little. But if you watch, I don't understand, but you let's move on. I don't understand, but you let's move on. You will see that you are moving on, you are adding the little, a little, and the little are compounding. Okay. Let's go to Esther.
So please, we are doing that to know the probability of only A happening or only B happening. With A intersection B, we'll be having both events happening in that.
Okay, so why are you doing the minus A intersection B?
So that we don't repeat the probability of A and B happening.
Good. And this is under what condition? So that you don't repeat. This happens only when A and B are what?
When A and B are joined.
Exactly. Okay. So when A and B are joined, so it means that certain events can be joined, certain events cannot be joined. So you got to know which one is joined before you apply the addition rule. Let's move on. Now, this is a joint and this is a disjoint. Okay. This is the disjoint. And because you don't want to count them twice, that is why you make sure. Now let's apply this to a deck of cards. You all remember a deck of cards. I know some of you didn't go through the access, but I want to believe that you still remember a deck of cards. Now, I could have spoken about a deck of cards, and it's possible that some of you will not even remember. Because you see, these days, the internet is taking over our lives. So we don't even play Ludo, Dummy, a deck of cards, the one we used to call Spy. We don't play. Do you remember Snake Ladder? Do you remember Snake Ladder?
Yes, please.
Yeah. When did you last play Snake Ladder? Some of you have forgotten.
We still have it in our homes, so we do play them.
Oh, okay. Say, I do play them.
Okay, I do with my children.
Exactly. because you are not an internet family all the time. You see, most of the people here are internet driven, and the internet driven people do not have these kind of games. Well, it's always nice to have these things because they teach you a lot of things, especially a deck of cards. Anyway, for your information, the deck of cards has got 4 S's, as you can see here on the first one. It's got 4 2s, 4 3s, 4 4s, 4 5s, and 4 10s. But it's also gotten 4 jacks. It's also gotten 4 clubs. Okay. And then, did I say 4 clubs? 4 queens. Okay. And then it's got 4 kings. But each one of these will be either 13 clubs or it will be 13 hearts. Okay. Or it will be 13 spades, or it will be 13 diamonds. In case you've forgotten, the diamonds, we used to call it calo. Do you remember those things? Calo. And then the hearts,
Yeah.
we used to call them yet.
Yet.
And then the spade, do you remember how we used to call them?
Spa.
Spa. And then the clubs, do you remember how we used to call them?
Queen.
Kulain. You see, when you're even mentioning Kulain, you are smiling. Because it's been a long time you started using these things. Well, we are going to learn that. I want you to know the numbers of each. The Kulains or the clubs are 13. The Kalos or the diamonds are also 13. So for each one of them, when I speak of jacks, you should know that they are 4. When I speak of queens, you should know that they are 4. When I speak of kings, you should know. But when I say that a king of hearts, then you should know that there are how many? Is 1.
1.
Just 1.
So you should know these things because we're going to think through about them. We're going to use them quite a bit. That's why I decided to bring the pictures here. All right. Now, let's get deeper. From a deck of cards, this is a very well shuffled cards. Okay? You shuffle them. Some people are very good at shuffling. You pick a card at random. What is the probability that the card you selected is a king or a queen? How would you go around that? Don't give me an answer because you give me an explanation. You're a teacher. What is the probability that if you select from this deck of cards here, that card, I mean, when you see the picture, it becomes easier, but you don't always have the picture. What is the probability that that card is a king or queen? And by the way, how many kings are there? Here.
There are 4 kings.
And how many queens are there?
There are also 4 queens.
So what is the probability that the card is a king or queen? What do you need to look out first before you even start? What do you need to, because if you can tell me what you should look out first before you even try to solve this, then I know you understand. What do you need to look out first before you start this? Marilyn.
Look out for the total deck of cards, the number of cards that we have.
Yeah, we know that one. Okay. That's standard. You got to look out for that. But there's something you need to look out for before you even start, because it's said king or queen. Josephine.
So we have to look at whether they are mutually exclusive or joint.
That's it. That's key. So now I ask you, don't run away. King and queens, are they mutually exclusive or they are not mutually exclusive? Are they disjoint or joint?
I think they are disjoint.
They are disjoint. Explain why.
Because if we are shuffling the cards, we can't pick both queen and king at the same time. We'd have to pick one of them at a time.
Very good. Or let's say that a card that is a king can also not be a queen at the same time. That's what you mean. Is that what you mean?
Yes, sir.
Card that is a king cannot be a queen at the same time. So these events are, yeah, they are mutually exclusive. Okay, good. If they are mutually exclusive, how would you solve this? Knowing the numbers. By the way, the total number is 52, and I know you all know that. So what would be the solution to this? The probability of using the additive rule, because you got to use the additive rule because the additive rule is the OR. The OR is additive. How will you solve it? This is how you go around it. Okay. So first, let's allow king, okay, K to be the king. And we know that there are 4 kings. Let Q be the queen. And we know that there are 4 queens. Good. So the probability of getting a king is 4 over the total, which is 4 over 52. And the probability of getting a queen is also 4 over 52 because there are 4 queens. So you add this 4 over 52 together. It's 4 over 52. And then you sum them. But remember, they are mutually exclusive, so you don't need to subtract anything. And that will give you this situation that you have here. So you can see that you're going to get 2 over 13. When you cancel it all out, you get 2 over 13. This is simple. Let's go to the next question. What is the probability that the selected card is a king or a diamond? What is it about this that you have to check first? What is it about this that you got to check first, Frederick?
You have to check if it's a joint. If it's joint, that's the probability, or if the event can both be a king and a diamond.
Very good. So you have to check whether they are non-mutually exclusive or they are mutually exclusive. So let me ask you, are they mutually exclusive or non-mutually exclusive?
They are non-mutually exclusive.
Good. Now, why? The rest of you who are not following, listen to him. Why would you say, oh, by the way, when we say that non-mutually exclusive, what we mean is that they are joint. When you always look at it from that and you transfer that to the tree language, it makes it easier, isn't it? They are joint. They are joint. That makes, instead of mutually exclusive, that sounds like Hebrew a bit. Okay, so my good friend, explain why you say so.
You can pick a card that is a king of diamonds. It's both diamond and king, one card. Yeah.
Exactly. So you can pick a card, and that card is not only a king, but is a diamond king. And that is why we know that they are. So you got to be careful that if you want to find the union, the union, then you got to not do double counting. Okay. So what is the probability of getting a king? You can tell us. What's the probability of getting a king, Selassie?
4 over 52.
4 over 52. What's the probability of getting a diamond? Selassie?
13 over 52.
Exactly, because there are 13 diamonds. Now, because you have done this, if you want to combine them, you have to take into consideration the union. And then you take out the intersection. So what is intersection of king or diamond? What's the intersection? A card that is both king and a diamond at the same time. So that's it.
So that would be 1 over 52.
Exactly. So that is what you will minus from the whole. Whilst you add the whole, minus the 1 over 52. That, this is how you write it. The probability of K union D, that's a king union diamond, is the probability of having a king plus the probability of having a diamond minus the probability of a card being both a king and a diamond. And this will be equal to 1352 minus 152. And therefore, your overall probability is 4 over 13. This is one of the simple or simplest addition rule. Now, this is a general one. The one we looked at before is not general. But this is general. So when you say king or queen, that one is easy. But this one is not, because there are multiple of these intersections all through. You can have a queen or diamond, a jack or diamond, and there are multiple of this instead of king, queen, jack, and all of that. They are just few. Okay, who is not clear with something? Let's move on then. Another rule of probability is the multiplication rule. The multiplication rule is not like the addition rule. The addition rule looks at mutually exclusive and non-mutually exclusive. The multiplication rule looks at independence and non-independence. Independence. Two events, A and B, are said to be independent if the probability of A given B has occurred is the same as the probability of A. This is very important because we'll come back to this when we go to the Bayesian theory. And by the way, even if you have the slides, my advice to you is to be writing whilst I'm talking. Write what you see on the screen. And the reason is because the human mind is the most unexplored continent in the universe. As you are writing, research shows that there is an information symmetry between your fingers and your brain, especially the cerebellum of your brain. And so as you are writing, your hands are connected to the brain. And so you have a neurological picture of what you are writing. And so even when you are forgotten, the neurological visualization gives you the thing when you are trying to remember it. Remember, a picture is worth more than 1,000 words, but it's a picture with an action. So what you are seeing, you're just watching, but you're not putting an action to it by writing. So it's good to write because it helps you to understand this a lot. Okay, so the multiplication rule says that independent events are in such a way that probability of A given B is the same as probability of A. Now that is seriously something. Okay, but more importantly, if that is the case, and we know that already, then the independence says that the probability of A intersection B is the probability of A times the probability of B. Okay. This is a rule. It's a rule. You understand? It's a rule, like gravity is a rule. And so, but the thing is, I can prove this rule. You can prove it. And there's a beautiful way of proving it. I don't want to go into the details of that, but I want to give you the general, independence rule. It says that if you have a family of events A1, A2, A3, all the way up to AI, if you have these events, which can also be written as A subscript I, where I is a member of the entire set of events. If these events are independent, okay, for all subsets of J, then we have this family as the general rule. So it means that the probability of the general event, okay, that is what we call the geometric coagulation or the amalgamation of all the events, is equal to the probability of each of them, put together. And that would also mean that because we are looking at each event, that would mean that the probability of A intersection, any one of them, okay, all the way up to the intersection of the final one, is going to be the amalgamation of A with the intersection of all of the rest. This independence rule, this general rule, you will not fully understand until I take a portion of it. It's not just 2 events, but maybe I take 3 events, then you can appreciate it more. So let's look at for 3 events. So for 3 events, what it means is that it is possible for A1, A2, and A3 to be independent. It is. Sorry, it's possible for A1 and A2 to be independent. It is possible for A2 and A3 to also be independent. Okay. And it is also possible for A1 and A3, that is crossing, to be independent. But it doesn't mean that A1, A2, A3 are all independent. No. That is the principle of the independence rule. Okay, so this guy and this guy are friends. This guy and this guy are friends. This guy and this guy are friends, but it doesn't mean that all of them are friends. Would that make sense? Does that make sense? Yeah, it does. It can happen. And that is it. In other words, there is no transitivity. Okay, that's another way of looking at it. Transitivity in the independence. Let's take a typical exercise for you to appreciate it. This is for just 2 events. You roll a dice, a 6-faced dice. You roll it not once, you roll the dice twice. What is the probability of getting 2 aces? 2 aces is those people who roll dice and do a lot of die games, the aces are called ones. You have aces. Sometimes you have aces. You have some other strange names. What are some of the strange names? Anyway, there are some deuce. Yeah, you have aces. You have deuce. You have tray. You have kata or sinking. All of these are some names that they use in the game of dice throwing. So ones. What is the probability of getting 2 ones in a row? You want to 1, especially when you're playing the Ludo. What is the probability of getting that? Well, independence come to the 4 here. First of all, what is the omega? What is the sample size here? Selassie.
Yeah, 6.
Good. So you have the sample size to be 6. And we are looking at the probability of getting ones in a row. Now, what is that probability of getting ones in a row? This is the probability of getting ones in a row. The probability of getting 1 in the first row is going to be 1/6. The probability of getting 1 in the second row is also going to be 1/6. And since we are looking at the probability of getting 2 ones, that is independence, in a row, that is going to be a multiplication of the probability of getting 1 in the first row or ace in the first row, and getting an ace also in the second row, which then gives you 1/6, 1/6, giving you 1/36. In other words, the chances of you getting even 1 in the first row is higher. The chances are higher because 1/6, higher than the chances of getting 1 in the first row and 1 in the second row. That's tough. That's why it's 1/36. 1/36 is smaller than 1/6. Independence is at work. Let's take another example. This one is more practical. The probability that you will get A in statistics is 70%. The probability that you will get A in machine learning is 50%. Assuming these 2 events are independent, find the probability that you will get an A in both subjects. Solve it and let me see. Who can walk us through how to do it? Who can walk us through? What are we doing? What are we basically doing? What are we going to do? What mathematical symbol are we going to use? And why are we using that mathematical symbol? What is a mathematical symbol and why are we using that mathematical symbol? Yes, someone. Yes, Ami, your hand is up. Was it a mistake?
No, Prof, sorry, it wasn't a mistake. I forgot I didn't unmute myself.
Okay.
Please, I think we ought to use multiplication in this case.
Why?
The reason is we are looking at the fact that the conditions here are independent. It means that one occurring doesn't affect the other. And then these are they are not joint. So the fact that you are getting A in statistics doesn't affect the fact that you are getting, and you are talking about you getting both an end condition. So the the arithmetic, there should be a multiplication, I think.
Okay, so how do you do it?
Okay, so the probability that you get A in statistics is 0.7. So, and
How
that
do you write
of
that,
machine
by the
learning
way?
is 0.5. So P, okay, so P bracket S, I'm using S for the statistics, multiplied by P bracket M if I'm using M for the machine learning. Okay, yes.
Don't worry.
Okay, so in this
I
case,
decided to use B,
yeah.
but it's okay.
Okay, so the next thing I'll do is we bring out the figures. So P of A is 0.7, P of B is 0.5, so I'll multiply.
Good. So now I want you guys to understand something here. What does the 35% mean? And I don't want you to tell me in statistical language, probability language. Now, what does that mean? Don't complicate it, simplify it. What does the 35% here mean?
It means it's unlikely for you to have both A in both subjects.
Exactly. That's the language. It's not easy. I mean, you guys are doing how many subjects?
6.
I do 6.
6. Do you think you will get A in all of them? I mean, this time you are talking about fate, eh? Which of you think you are going to get 6 A's? Be bold. Be bold. Massa, don't bring God yet, but you be bold. You see the VIM? The VIM is a clear indication of even the probability. You see, some are still going to now by force raise their hands. So when they know inside their bone of bones that the VIM no day, the probability of you getting A in one of the subjects is cool. But the probability of you getting getting A in both statistics, machine learning, programming for analytics, and the others, that is cool. That is lovely, interesting. So you can see that the chances get smaller as you are going because it's not all that likely. This is why you see this kind of probabilities. Okay, now let's move on. These are events that are dependent. But what if the events are not dependent? So please note, the reason why you knew that you have to use multiplication for the previous one was because you were told that the events are dependent. If you were told that the events are mutually exclusive, then you know that this thing is not the multiplication rule, but it's additive rule. So how the question is, how the information is, will guide you to know what to have. Okay, let's look at it. Independent. The non-independence rule says that the intersection must be taken into consideration. So the probability of A intersection B is the same as the probability of A multiplied by the probability of B giving A. That giving means that the probability of B giving A is the conditional, so it's conditioned, is the conditional probability of B given that A has already occurred. Now watch that word, conditional probability, because that conditional probability is going to cut across and help us with the Bayes theory. So let's take an example where this becomes apparent. And again, look for the word that will help you to know that this is a non-independent event. Of course, you don't know whether it's mutually exclusive or not mutually exclusive. That is additivity, but this is multiplicative. 2 cards are drawn in succession, one after the other. After every draw, the selected card is not replaced, but they are drawn in succession, but it's not put back. What is the probability that in both draws, you will get spades? Now, if you look at this question, what gives you the clue that this is a non-independent event? Or better still, dependent event. What gives you that? What is in the story? It's not about Mutually exclusive or not mutually exclusive, it's about independence here. What gives you that? Johannes?
So it says that after every draw, the selected card is not replaced.
So
that means they are independent.
Let's go to John.
Yeah, so it says that the cards are not replaced, which means that it's going to affect the total for the next draw of card. So it's dependent. So the next draw of card is dependent on the first one, because after the first one, it's going to affect the total.
Exactly. Guys, this is dependency. Because you said I didn't replace it. So if the cards were, say, 52, and then I picked the first one, I did not replace it. When I'm going to pick the second one, the cards are no longer 52. The cards are now 51 because I didn't replace the first one. So the probability of getting that second card is going to be affected by you removing the first card. The chances are going to be affected. So they are dependent. And in such a dependent situation, how you calculate the probability, you see, because the last thing is that what is the probability that in both draws, you will get a spade. So now let's look at spade. How many spades are there?
Yeah, 13.
13. 13 spades. Now, what do you think is the probability of getting a spade in the first draw, in the first drawn card?
That
What
would
do you think
be
is that?
13 over
Who is
52.
talking? I've not seen the hand raised.
Sorry, sir.
Let me give it to Selassie.
So the probability will be 13 over 52.
Okay, what about the second one?
That would be 12 over 51.
Exactly. Okay, so this is how you compute your probability. So you can see that the second one has been affected, even the denominator has been affected. And that shows that there is dependency here. Okay. And then on the basis. So what is the name of that second one? That second one is a probability of getting a second spade, given that you already have the first spade. That is why you see the giving symbol there. Okay. And this one is a very powerful, this rule is the both. So anytime, what is the probability of getting both draws? This rule of multiplication at the top happens because of dependency. And when you now take it, you can now multiply it and you'll get your 1 over 17 in that. You see, when I give you multiple probability questions, your job is to be able to read in between. Is there dependency? Is there no dependency? Is there mutually exclusivity? Is there no mutual exclusivity? That helps you to know which rule to apply. Remember, the addition rule has two. One is where you add them, you don't look at the intersection. One is where you add them, you take care of the intersection. The multiplicative rule is also two for conditions. Okay. One is where you multiply them, you don't take care of the condition. But the other one is when you multiply them, you take care of the condition. Remember, these are rules. Let's move on. And now define proper conditional probability with this. So we have two events, A and B. Both of them are going to give you positive probabilities. The probability of B is positive. The probability of A is positive. Now, the conditional probability of A occurs, given that B occurs, is written as the probability of A given B. And this is how you define conditional probability. Now, please remember, this conditional probability is something you already know from the dependence rule. The dependence rule. So this is it. How do you write it? The probability of A given B, and this is a rule. When I say it's a rule, it means I got to memorize it. Of course, it must make sense to you, but you still have to memorize it. Don't worry. These rules are things that you should know, okay, at a master's level and apply it. Probability of A given B, the rule is that it should be the probability of A intersection B divided by the probability of B. And look at it and write it. Look at it and write it again. Because as you are writing it, you see, writing this thing like this is not a crime. You are writing it in your book. What you don't know is that while you are writing it like this, A intersection B, your brain is taking the thing in a more powerful way. I'm telling you. And so your brain absorbs the content and you're able to better understand how it works. Always write things down. Okay. So this is the conditional probability. Now we can do some manipulation of this conditional probability. It's a rule, but you got to know that you can prove it. Okay? It's a theory, and you can prove it. You can prove it, okay? Because it's easy to show that this new probability operator, this true conditional probability operator, satisfies probability adjectives. We can prove that. Let's get a proof of this first one. Do you remember the condition? Go back here to the multiplication non-independence rule or the dependence rule. Okay. This was the condition, probability of A intersection B. This was A intersection B. Look at it carefully, A intersection B. And that was probability of A multiplied by the probability of B given A. If we divide both sides by probability of A, do you realize that the probability of B given A is going to be probability of A intersection B over the probability of A? Do you see that? I need to know whether you see that before we move. We come
Yes,
to.
please.
All right. Keep that in mind and come here. Do you see that that's the same thing here as a conditional probability? Or you don't see?
Yeah, it's clear.
Is that clear?
Yes, please.
Okay. I've told you guys that if you don't get it, you say it here. So this is as a result of manipulating the dependency rule. And this one can then be proved. So it means that when you come here, the probability of A giving B is probability of A, which therefore implies that the probability of B giving A is the same as the probability of B. Now, watch this. I am saying that the probability of B giving, or the conditional probability of B giving A is a probability of B. Let's prove that. First of all, we know that the probability of B giving A, just like the top, I've just switched them, is the intersection, the probability of the intersection of A and B over B and A. Now, if you look at the probability of A intersection B, you should know by now that it's the same as the probability of B intersection A, because the intersection is intersection. Okay. So A, if this is A and this is B, and you have intersection here, intersection is intersection. Okay. So intersection is intersection. So it means that the probability of A intersection B is the same as the probability of B intersection A. Intersection is intersection. That is why even though I swap this and that, I am maintaining this and this. And of course, I swap this and that, I'm maintaining the intersection because intersection is intersection. Keep that in mind. Now let's go back to the proof. So with that in mind, we can say that with this, we can say that this very thing is equal to that. Okay, is equal to this. This is a conditional probability that we define. Okay. And then we can say that using the multiplicative rule, we can break this thing down. Look at it. The probability of A intersection B is the same as the probability of B multiplied by the probability of A given B. We knew that from the conditional probability. Okay. Let me just circle it for you to see. This one is the same as this. It is the same from the dependency rule. How do we know that? Look at it. It is an intersection, and this intersection is the same as it. We knew that from before. So when you substitute that here, now we can now break this thing down. Watch it. We know that if you have the probability of B, multiplying the probability of A giving B by the rule of multiplication, we would also note that the probability of B multiplied by the probability of A giving B is the probability of B times the probability of A. It's the same, again, giving that rule. And so if you substitute this one here, you can now cancel this, and now you'll be left with the probability of B. That is why we concluded here that the probability of B giving A is the probability of B, which is this, which matches, the conditional probability. So what this means is that understand this. This rule is very important. Probability of B giving A is the probability of B. The same way that probability of A giving B is the probability of A. So wherever I see probability of A giving B, I can put probability of A. And wherever I see probability of A giving B, conditional probabilities, I can put in that. This conditional element, this is just theory that we are knowing. But now let's get practical. Okay. Practical. It's not all the time that you have to use the rule. Sometimes you can even look at it and you don't even need to use the rule. But sometimes one can use the rule. Other times you can just think about how the B has changed the sample instead of finding the A intersection B and calculating their ratio. This is a typical example of that. A deck of cards is well shuffled and two cards are drawn without replacement. What is the probability that the second card is a king? What's the probability of the second card? The second, not the first. Now, first of all, what is the probability of getting the first card? You can tell. The first card. What is the probability that the first card is a king? David?
Say 4/52.
Okay. Now, that is true. 4/50. So the probability of getting the second card is what? The probability of getting the second card.
3/1.
Again?
Because you drew the first card and you did not replace it, it reduces the sample space to 51. And then the one is already on. So you'll be left with 3/52.
Now, so I think I made a mistake here. Okay. So the probability of getting, this is a very simple one. Okay, the probability of the first card being a king, which will be the second card, is 351. Given that the first card is not a king, it's going to be 4/51. Okay, so that means that the second card is going to be 3/51. This is just coming from your head. You didn't apply any rule. Okay, so it's just a way to let you know that you can work out your probabilities without applying any rule. But you have to apply rules sometimes. And when you apply the rules, okay, it makes it easier. This is another way you can apply the rule, or you can choose not to apply the rule. Oh, let's go to Magdalene.
Doc, please, good morning. You said the first one is 3/51. I thought that is going to be 4/52.
4/52. I said I made a typo with the second by writing the word first.
Oh, okay. Thank you.
Yeah, by writing the word first, it should be second. Okay. Because this is giving that the first card is already taken. So this is the second. Magdalene, do you understand?
Yes, please. Yes,
Watch
please.
the word.
Thank you.
The word is given. So given that the first card, which is the 4/52, has already happened.
Oh, okay. Okay, sure. Thank you.
So the 4 over 52 has already happened. That's the first one. Now, given that that has already happened, now we are talking about the second card. The second card is 3 over 51. That is given that the first one has already happened. All right. John, your hand is up.
Yes, sir. So I think I've got a bit confused. So the question is saying that a deck of cards is well shuffled and two drawn without replacement. So what's the probability of getting if the second card is a king? So it means that when we are first calculating what's the probability of drawing the first card, I think for the first card there was no specification as to whether the first card is going to be a king or not. So in my mind, the
No,
probability
you
of
got to
drawing a
assume.
first card.
Okay, go ahead.
Okay, so like in my mind, the probability of drawing a card first is supposed to be like 1. Because if
1 over.
no, like 1. So it's like 52 over 52, which will give you 1. Because it wasn't specified whether the probability of drawing the first card is going to be a king. So it was just saying that was the probability of drawing the first card. And the probability of drawing a card is 1. Before that, we move on to the probability of drawing the second card being a king.
So yeah, so what was your question?
Yeah, so my question is the probability for drawing the first card. It wasn't specified. So do we have to specify it as maybe probability of drawing the first card is a king? Because the question didn't specify if the probability of drawing the first card is a king.
Well, the thing is that if he's talking about the second card is a king, okay, you got to make an assumption that the first card was a king. I know it didn't specify. Okay. Other than that, what you're going to do is that you will not know what the second card is in terms of probability. Otherwise, I ask you, how would you have found the, okay, so if you pick the first card, okay, and the first card, the first card is not a king. What is the probability?
So the probability is going to be 52 minus 4.
Exactly.
So 48.
No, 52 minus 4, 48 over 52.
Over 52, yes.
Yeah. So that will be 48 over 52. That is when that first card is not, when the first card is not a king. Now, what if the first card is a king?
So that'll be 4 over 52.
That'll be 4 over 52. So what if the first card is a king, and now the second card?
So that'll be 3 over 51.
It comes back to the same thing I'm showing you here.
Okay. So that means we have to assume that the first card was a king.
Yeah.
Okay.
Yeah, because it comes back to the same thing as you can see here. Because if I take this one out, now if you assume that the first card is not a king, you are going to get, what do you call it? Is it 48 over 52?
Yes, please.
Yes. So, but you don't know the card.
Yeah.
But you only know that it's not a king.
Yes, sir.
But we still have picked a card. So we know it's a card. But I'm not calculating 48 over 52. I'm not calculating the probability that it's not a king.
Okay.
I'm calculating the probability that it's a card.
Okay. Is that calculating that the probability is a card? That is a 1. Because that would be 52 over 50, because definitely it's a sure probability.
Yes. So that is 52 over 52.
Yeah.
So what do you think is the probability that the second one is a king?
So the probability that the second one is a king will be 4 over 52. sorry, 4/51. No, 3/51. Yes, it makes sense.
Conclude again. It's going to be what?
So it's going to be 3/51.
There you go. That's why I'm saying that at the end of the day, you come back to the same thing. Yeah.
Okay.
That is why you got to assume what the card is. It's going to be one card anyway, isn't it?
Yeah.
Yeah. Yeah, if the share of it is 52, it's still going to be one card anyway. Yeah. Anyway,
Sure, thank
let's
you.
move on. I saw another hand. Whose hand was up? Okay. Let's go to a practical one. Okay, very practical. We have a cross-classified faculty members in a certain university. The faculty members have been classified according to their age as well as according to their rank. Your ranks are full professors, associate professors, assistant professors, and then lecturers. And then the ages are those under 40 years, 40 to 49, 50 to 59, and 60 plus. Question. What is the probability that a person, a faculty member, is a full professor, given that he is under 40? It's very simple. This one, you can just look at it, but then we'll use a conditional also to confirm. What's the probability that the person is a full professor and also he's under 40? Given that he's under 40, by the way, given that he's under 40. I need more hands. With your eye, look at it with your eye. Given that he's under 40, what is the probability that the person is a full professor? Afia?
Please, that would be 54 over there, total, which is 470.
Good. Why did you use the total?
All those under 40, that is because that's their sample total. All the lecturers, the total lecturers under 40.
Yeah, I get you, but why did you use 1164? Why didn't you use the 470?
It's independent.
What do you mean?
So she used the 470. She didn't use 1164.
Oh, she used a 1164.
I saw over 470.
Oh, you said over 470?
Yes, please.
Okay, then that's rather wrong. See, I was thinking that you've used the correct one, and I was rather trying to justify the correct one.
Okay.
Okay, so now watch this. You can look at it. First of all, before you, that word, given that you are under 40, if you're under 40, okay, then you already are in this row, in this section. But the thing is that, don't forget that the thing is that you got to be a faculty member. That's guaranteed. You got to be a faculty member. And as long as you're a faculty member, it means that you are in the school, you are in the university. Okay. So, sorry. Did you say you use 470?
Yeah, so she's right.
Yeah, she's right. I think I was confusing myself with that. Okay. So you got to be a faculty member, and you have to be someone who is under 40 years. And so first you select those who are under 40 years, and then from there, from that 40 years, you select those who are under 40. As you select those who is a full professor. So you pick the person who is under 40, and then after that, you pick the person. Now this one, you can look at it and say it. But I'm more interested in when you don't have a table, because when you don't have a table, how do you justify it? Yes, John.
Yes, so the question is to find the probability of full professors, number one, and then the next thing is the person should be under 40. So
yeah, the
why
person
are
should
we
be under
not
40
using,
first.
okay.
That's
So
why
why
it's
are we not
given.
using the total of the full professor, that's the 430 instead?
Good
So
question.
out of the total of the full professors, then we
Good question.
choose 54.
I would have thrown it back to you, but because of time. The reason is because first, you are getting the probability of a person being a professor, given that that person is already under 40. So first of all, don't even look at a full professor yet. Don't go and look at the 430. But first, go and look for those that are under 40 first. And so those that are under 40, let's come here. Those that are under 40 are these, because that is where they're given. That is already happened. So let's get those that are under 40 years. Okay, now that you got those that are under 40, they are 470. Now, out of that, let's look out for those that are full professors. So the full professor is conditioned on you being under 40. Does that make sense?
Yes, please, it does.
Okay, now that is by looking at it. But you can use a conditional probability to also do the same thing. By definition, you can say that the probability of being a full professor, given that you're already under 40, is an intersection of you being a full professor and you being under 40. And you check it, the intersection of you being a full professor and you being under 40 is 54 over 1164. Then, and this is the conditional probability that we have already done. If you go up here and check the conditional probability, this is it. You have to take the intersection here. Let me delete this. This is the formula that we are looking at, okay? Given that, so you have to take the intersection divided by the under 40. Remember, the under 40 here is given. The B is under the 40, is being given. So you can use that same formula now to indicate that given that you're already under 40, the probability of you being under 40 is 470 divided by 1164. And so when you take this one, you still get a 54 over the 470. So my point is that you are supposed to understand that the probability of you being a full professor, given that you're already under 40, you have to always keep it in mind that is the probability of you being a full professor intersection under 40. You got to have that intersection under 40. So that intersection divided by the whole, then you take the probability of you being the given one, okay, which in this case is under 40. And that will eventually come to you getting the same answer. This is a conditional probability. But you picked the answer without using the conditional probability. But you can use a conditional probability to also arrive at the same answer. Okay, let's get to the end by looking at the Bayes theorem. The Bayes theorem. Now, the Bayes theorem is not going to be difficult because we are combining everything we have done. This is a theory that was developed in the 1700s by Thomas Bayes. Let us have event A and event B as two separate events. The Bayes theorem says that the probability of A, the conditional probability of A, given that B has already happened, is the probability of B, given that A has already happened, multiplied by the probability of A, all divided by the probability of B. Now, let me tell you something. It's a theorem. It's a theorem. So sometimes when people, some students who don't like probability topics or things, they say, why? There is no why. I can prove to you that it's a theorem. Why? Like when you throw things up into the air, it will come down. Okay? Because there's a theory called the theory of gravity. There's a theorem of the theorem of gravity. Then you say, why? Why? It's a theorem. It's a theorem. And so this is a theorem. Now watch the theorem very carefully. The conditional probability of A given B, in that formula, you also have the conditional probability of B given A. Take note of that part. That's a key part. So I want you to tell me the conditional probability of B given A, but also remember that I would have given you the conditional probability of B given A. Tell me the conditional probability of A given B. But you should already know the conditional probability of B given A. Tell me the distance it travels from Accra to Kumasi. But I would have already given you the distance it takes from Kumasi to Konongo. So you would have the conditional probability of A given B, okay, but you should use that, the conditional probability of B given A, but you should use that to find that of A given B. Of course, with other things involved. And you can switch them the same way as you can see here. Let's try to understand this because it comes from the conditional probability theorem. The Bayes theorem comes from the conditional probability theorem. If you take the conditional probability theorem and revise it slightly, you can now arrive at the Bayes theorem. Let's take the conditional probability theorem. This is a conditional probability theorem. This one here. This theorem, what is that? This is it. We already know this, that the probability of A given B is equal to the probability of A intersection B divided by the probability of B. This is the one we just used to solve the professor and the under 40 question. This one. I hope you all remember it. Now, we are going to manipulate this slightly. We are going to switch A and B. We're going to switch A and B. Okay. We're going to swap them. So wherever we see A, we put B there. And wherever we put CB, we put A there. This is it. Check it and see. And you see that probability of A given B, now we have probability of B giving A. Now these two are both conditional probabilities, but they all manifest. Okay, it's about which one comes first and which one comes second. I did not say that they are equal yet. I did not say that. Now, with this in mind, we can do some interesting manipulation. We already know that the probability of A intersection B is the same as the probability of B intersection A. We've done this multiple times because they are in the intersection. And once they are in the intersection, it doesn't matter which one you bring first. B intersection A is A intersection B, so their probabilities are the same. We know that. If you don't get any one of them, let me know. Now, if we replace the probability of A intersection, B intersection A here with the probability of A intersection B, then we can cross multiply. Okay. So if you look at this B intersection A here at the top here, we can replace that with probability of A intersection B. And then after replacing it, we can swap them. Now, I am replacing it because it's the same, because the rule here says it's the same. So now I'll go back here, and then in my formula here, instead of writing probability of A intersection B as a numerator, I rather write probability of B intersection A. And now I can cross multiply them, which means that this probability, let me just go. It means that this probability of A giving B will multiply the probability of B, and that should be equal to probability of B intersection A. Now, with that in mind, we can now say that, and this multiplication is what I've just done here, we can say that the probability of A giving B multiplied by the probability of B is equal to the probability of B intersection A. That's what I just said. But now connect that to this one above here. Okay. If you connect that carefully, do you see the trend now? You can now see why this top part is equal to this down part. Because you will notice that if you have B intersection A here, and then you have B intersection A here, then when you multiply, watch it carefully, they are all B intersection A, B intersection A, okay? But when you come to this side, you rather have probability of B, because when I multiply this one too, you have probability of B giving A, multiplying probability of A. But here you're having probability of A giving B, multiplying that. So it means that if I connect these two are equal, and therefore these ones two are equal. Guys, are you with me? This one and this one are equal. So the multiplication of this and that is the same as this multiplication of this, that. And therefore, wherever I see the B intersection A, I can replace any one of those. That is why in here, that B intersection A, which is a conditional probability, or A intersection B, whichever one it is, I can then choose to replace it with this. That is what you have here as probability of B intersection. A B given A multiplied by the probability of A. Does that make sense? I should go over.
Yeah, it's okay.
Good. So that is how, yes, John.
Yeah, so sir, can we go on further to say if the probability of A given B is equal to the probability of A? So then can we further on say that the probability of A given B, which is equal to probability of B given A multiplied by probability of A divided by probability
All of that
A.
is equal to the probability of A.
Yes.
Yes.
So we can say it's for the numerator, probability of A B given A, we can change the probability of A. So we are going to have probability of A squared over probability of B, and then the other one probability of B squared over probability of A.
Yeah, you can. Yes.
Okay.
You got it. Yeah, you get it. So now, so this is a theorem. I just wanted to prove to you where the theorem comes from, and it comes from the conditional probability, as we know. With this knowledge, we can now see certain things in life that actually can be handled using this Bayes theorem. Let's take one of those things in life. Oh, by the way, the Bayes theorem, we can do a generalization of everything I said. If you have any particular event, okay, and there could be multiple of the events from 1 to infinity, those events can be partitioned. They are still within the omega, still the sample space. Okay? And then you can now have that, given that the probability, each probability is positive. This formula here is still the Bayesian theorem, but in a broader sense, in an infinite number of events within the sample space. So this is the generalization of the Bayes theorem. Now let's take a practical example. For those of you, I went through the access with you. You probably know about this. You have a drilling company, and the company has estimated a 40% chance of striking oil for new well. So watch the words carefully. There's a 40% probability. So the probability is already there of striking oil for the new well. A detailed test has been scheduled for more information. Previously, 60% of successful wells have had detailed tests. So 60% of successful wells, so the wells are already successful, okay, but they've had detailed tests. And 20% of unsuccessful wells have also had detailed tests. So given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? Now watch it carefully. There are some conditions here. There's a conditional probabilities here. Let's pick them one by one. Which one has been given, which one have not been given, that we have to find. Well, the one that we have to find is that given that this well has been scheduled for a detailed test, so what has been given is that the well has been scheduled for a detailed test. It's been scheduled for a detailed test. Given that, what we are looking for is the probability that the well will be successful. Now watch here. 60% of successful wells have been detailed. of have had detailed tests. Now, this is the opposite of what we are looking for. What we are looking for is if there has been detailed tests, what is the probability that it will be successful? But what we have here is that 60% of successful wells have been detailed. But what you are looking for, given that they have been detailed, what is the probability that the well will be successful? But what you have here is the probability of it being successful, given that it's been detailed. Okay. 60% of the successful wells have been detailed. So 60%, the probability that is being detailed is 60%, and based on that, it's successful. Okay. Now we are looking for what is the probability that it will be successful, given that it's been detailed. So you have this 40% probability, you have this 60% conditional probability, and then you have this 20% conditional probability. How do we go about in handling this question? The first thing you got to do, first, you got to find the probability, or the let S be successful wells. And then you find the probability of S. So who can tell me S is wells that are successful? What is the probability of having successful wells? And of course, you are going to explain why you chose that. What is the probability that a well is successful? You can see that from this story. Who can tell me? What is the probability of S? If S is successful well, what is the probability of having a successful well? General probability of having a successful well on this. Yes, Dovi.
So that's from the question, that is 40%.
Good. And you can see that from here. You say a drilling company has estimated the 40% chance of striking a well. That word striking a well means of being successful in getting a well. So the probability of a successful well is 40%. Keep that in mind. Now let us let U be unsuccessful well. Now from the story, what is the probability of having an unsuccessful well? You can see that. Oh, by the way, this first one, the probability of having a successful well is already given to us. That's what he said, is 40%. And you can see that from here. So striking the well is 40%. It's given. So this is called prior probability. Now we want the probability of having unsuccessful well, which is also given in the question. It's also prior. Abrefi.
Okay, I thought you were asking the question. I was even going to look at if there's a 40% chance of successful indirectly, then there will be a 60% chance of unsuccessful.
Oh, you want to go straight away like that? Is
So
that what
just
you
from the first part of the question, a drilling company estimated a 40% chance.
I know, but what I'm saying is that, are you using that to answer the overall question in blue?
Yes, for that was what I was trying to do.
No, you can't do that immediately like that, because you're not taking care of all the prior probabilities and the conditions.
Okay, sir.
So first, we just need to understand that the probability of getting a successful well is 40%. Okay. Now, remember that well would have had detailed tests already. Okay, and you don't know the detailed test of that. Okay, so that's why we got to take into consideration that. Now, the probability. Oh, okay. Unless you are talking about unsuccessful well related to the successful, is that what you meant? Is that what you meant?
So I'll just look. Yes, please. I'm not.
So what I mean is that, are you answering my question, or you are answering the question in the blue?
I was saying like just from the first part of the question, we say 40% chance. So at the end they will have 60% chance of unsuccessful.
I get you.
An estimated.
Thought you were answering this blue question, which is the probability that the well will be successful, given that it's been detailed. But you are answering, but you are answering the probability that the well is successful based on the fact that, sorry, it's unsuccessful, based on the fact that it's successful. Okay.
Yes, please.
Yeah, correct. So if there's a 40% chance of the well being successful, it means that there is a 60% chance of the well being unsuccessful. And you can deduce that from here. Now, these two have been given. They are prior probabilities. Now, because these two are prior probabilities, we need to now find two things, the conditional probabilities. Now, what are the conditions? Before the well is successful, we need to do a detailed test. Okay, so first, let's look at it. So the probability of the well being successful, which is a PS, is 40%, 0.4. The probability of the well being unsuccessful is 0.6. These are the prior probabilities. We need to now find the conditional probability because there is a condition that you have to go through before you become successful or unsuccessful. Let's represent that by D. So D is the detailed test. So now my question to you is, first of all, let's find this. What is the conditional probability that there is a detailed test given that is successful? Now, you will know that from here, from the question. Historically, 60% of successful wells, so given that is successful, okay, that's the 60% of successful wells have had detailed tests. So now the question is what is, and this is very important, okay, because this part is the conditional part. What is the probability that, or what is the conditional probability of a detailed test? Eves, you are controlling my annotation. I need to clear it. Hold on a second. Okay. So what is the conditional probability of a detailed test given that the test is already successful? Okay. What is the conditional probability of a detailed test given that it's successful? And you can sense that from there. Now, these ones are conditional probabilities because watch it. 60% of successful wells have had detailed tests. So 60% of successful wells. So the probability that a detailed test has been performed, given that it is successful, what is that? So let's see.
So that's 0.6, which is 60%.
Okay, so now my question to you is, what do you think is the 20%? What is the 20%? Of course, it's in the question, but what is it? What does that mean? How would you have written that in connection with what I wrote here about the probability that there is a detailed test given that it's successful? The well,
that would be the probability of a detailed test given that it is not successful or unsuccessful.
Correct. Okay. So the probability of a detailed test given, and this is here, 20% of unsuccessful wells have had details. So the probability of a detailed test given that it is not successful, is unsuccessful, is 20. So let's put that down here as well. Okay. So when you come here, you will see that the probability of D given S is 60% of D given U is 20%. Now, what is the question asking you? Watch it up here. The question is asking you, look at the top here. We know of P of S is 40%. P of U is 60%. We already have P of D given S, P of D given U. What is the question asking you? Let me just go back here. How would you have written that? What is the question asking you? How would you write that? How would you write that? Which one is given here? What is given? In the blue question, what is given? Salas, your hand is up.
So you are looking for the probability of success giving a detailed test.
Good. So what is given?
A detailed test.
Good. And what are we looking for? Successful or unsuccessful?
Successful.
Good. So how will you write that?
So it will be probability, which is P, so S giving D.
Exactly. The probability of S giving D. That's what you are looking for. And guys, watch it. This is a Tomatic conditional probability because the probability of X, let me just go down here so that you can appreciate it even more. This probability of S given D, I just want to wipe this and then I show you why it is conditional, because you already have all the necessary conditions that are there to be able to manufacture it. What this means is that you now have this probability of S giving D, and this is conditioned on the fact that you already have the probability of D giving S. Note that. You have the probability of D giving S, and you have that here. And that is multiplying the probability. Who can tell me what it's multiplying? Because this is where base, because you're using the Bayesian principle to do that. Okay. This is multiplying. Yes, Johannes.
So since the goal is to find the probability of success giving D or the S giving D, it is going to be the probability of D giving S by the probability of S.
Okay, good. So that is the first part. Now remember that this situation is not an individualized situation. It is multiple events. Yeah. And so because it's multiple events, you have to take each one at a go because each one was given in this context. So this will be divided by what? Ideally, if we were to go by the normal conditional probability, we would have just looked at the probability of the well. No, but we were not giving the probability of the well. We're giving the probability of successful wells and then the probability of unsuccessful wells. We're giving that. Okay. And we know that from here. Even here, you know that. Okay. And then we have the conditional probability of D giving S. We know that. So in order to be able to determine the denominator, and normally the denominator would have naturally been the probability of U. Okay. That is how it would have been. But you cannot just do that, or wells, not even U, but wells. But you can't do that. You have to take wells that are successful from wells that are unsuccessful. You got to put all of them together. So you have to do the probability of a detailed test, given that it's successful. Okay. That one alone should be multiplied by the probability of success for wells. Then you take the probability of a detailed test, given that it is unsuccessful, multiplied by the probability of unsuccessful wells. These two, because we are doing general, these two must be taken as part of the denominator before you can now calculate the conditional probability. So let's do that. Let's do that here. And then you can appreciate this conditional probability. It is a little bit detailed, but if you take your time, you'll be able to realize that this is how it is. Somebody's noise is on the screen. Where is it? Okay. So now you take this conditional probability of D given S multiplied by the probability of S. But then the denominator is not just wells. It is the wells are split into those that are successful and those that are unsuccessful. So that's why you got to combine these two, which is this formula. At this stage, you can just take each of the probabilities and multiply them. We know this one. We know D giving S. We know D giving U. We know S, we know U, we know D giving S, we know S. So it's just a matter of just multiplying. Yes, Frederick.
So please, I wanted to ask, based on this, does that mean that the denominator, we are finding like the equation of the denominator, the sum is equal to the detailed wells? That's both successful and unsuccessful.
Yes,
Okay.
exactly. The detailed well. Remember, it would have normally been just taking the probability of wells. Normally it would have been just for wells. But if you remember the general Bayes theorem, it requires you, okay, and again, if you've forgotten the general Bayes theorem, let me just take you back here. This is a general one. This one was a very specific one, okay, that has combined successful and unsuccessful wells together. Okay. But of course, not to talk about detail. Remember, the whole thing for this A and B is where you have one being detailed, one being successful. That's what you have. Okay. Detailed and successful. But then detailed and then wells. Detailed and well. But then with this one, the wells is split into successful wells and unsuccessful wells. Okay. So the formula you got to take is this very formula, where you have partitioned the event. And so you have the probability of A given BI multiplied by the probability of BI. That in our case was the successful one. That's in the one that we did. That is the one which is the detailed given successful multiplied by successful. So here, detailed given successful multiplied by successful. But then when it comes to the denominator, you have to take a sum of AB multiplied by the probability of B, as many of them as possible. But this AB, you had it for the detailed test given successful. So you have to go and look for detailed test given unsuccessful. Okay. Detailed test given unsuccessful. Okay. If there is another detailed test given, forget about successful and unsuccessful. If there was a third one, let's say almost successful, then you also have to add that almost successful to this one so that you have a multiplicity, a multiple of addition of conditional probabilities for the denominator before you can now calculate your work. And that is why when you come here, you will notice that we are adding the detail, because the detailed test was performed on both successful and unsuccessful wells. And so once you have that, you can't just take that of the successful wells and forget about the unsuccessful well, because you are taking the conditional probability of all of them. So you just have to go back. And one way you can know that you have to take all of them is that if you should take only the successful wells, you would have realized that it's useless. You didn't take into consideration. Look here. You would have realized that it's useless. All of these things that was given to you is useless. But anything that is in the question cannot be useless. Okay? It means that you did not even capture anything related to unsuccessful wells. And so you got to take both successful as well as for the unsuccessful wells. And that is what, if there was almost successful wells, almost, we would have taken that as well in addition before you calculate. That gives you this formula. In fact, the rest is just substitution, which gives you this very formula. And that shows that you have 66.7%. Okay, that is the conditional probability of having a successful well, given that it's been detailed. So the revised probability of success from the original one, which is 40%, given that this well has already been scheduled for a detailed test, is almost 70%. Go and look at this again. Look through again. It will help you get a detailed understanding of what we have looked at. Now, I will not start with the random variables today. We'll look at next time random variables, where we'll now move from all of this, and we will now look at simple applications, simple application. We look at binomial, we look at Poisson, we look at normal distribution. All these applications, we'll look at them before we go into the hypothesis. All right, any question? Any question on this?